Imagine powering your sensitive electronic devices directly from a wall outlet. That alternating current, or AC, is constantly changing direction and magnitude. But your phone, your laptop, even many medical instruments need a steady, unwavering direct current, or DC. The crucial process that converts AC into DC is called rectification. So, how do we get the cleanest, most stable DC from an AC source? Among the common rectifier circuits, the full-wave bridge rectifier generally offers a significantly better DC output compared to the half-wave rectifier. It provides a smoother, more consistent DC voltage with less ripple, which is essential for reliably powering most electronic devices. The superiority of the full-wave bridge rectifier stems from its fundamental operation. A half-wave rectifier only utilizes one half of the AC input waveform, blocking the other half. This results in a DC output that is pulsed, with large gaps between pulses, leading to a high ripple voltage and a relatively low average DC voltage. In contrast, full-wave rectifiers, which include both the center tapped and the bridge configurations, convert both the positive and negative halves of the AC input into DC pulses. This effectively doubles the ripple frequency compared to a half-wave rectifier. For a 60 Hz AC input, a full-wave rectifier produces a 120 Hz ripple, while a half-wave produces a 60 Hz ripple. This higher ripple frequency is a key advantage because it makes the DC output much easier to filter and smooth out using capacitors. The full-wave bridge rectifier, specifically, does not requiring a center tap transformer, allowing it to utilize the full secondary voltage, and typically offers a higher peak inverse voltage rating requirement for its diodes compared to the center tapped configuration, but uses for diodes instead of two. To further improve the DC output and make it even smoother, a filtering stage is almost always added after the rectifier. This is typically a capacitor connected in parallel with the load. Because the full-wave rectifier produces a ripple at twice the frequency of a half-wave rectifier, the filter capacitor has less time to discharge between pulses. This means that for the same ripple voltage, a smaller and often less expensive capacitor can be used with a full-wave rectifier. The higher average DC voltage and reduced ripple inherently offered by full-wave bridge rectification significantly simplify the task of achieving a clean and stable DC power supply, often followed by a voltage regulator for precise control. Quantifying this, we often talk about the ripple factor. The ripple factor for an unfiltered half-wave rectifier is significantly higher than that of an unfiltered full-wave rectifier, with typical values around 1.214 half-wave versus 0.484 full-wave. This numerical difference directly reflects the substantial improvement in DC purity. Another consideration is the diode voltage drop, usually around 0.7 volts for silicon diodes. In a full-wave bridge, the current passes through two diodes in series for each half cycle, resulting in a total drop of about 1.4 volts. While this is a small loss, it becomes more significant in low-voltage applications. However, the benefits of the bridge rectifier in terms of average DC voltage and ripple reduction generally outweigh this small voltage drop for most applications. Ultimately, when striving for a stable and efficient DC power source, the full-wave bridge rectifier stands out as the superior choice. Its ability to harness both halves of the AC cycle delivers a higher average DC voltage and a ripple at double the input frequency, making the subsequent filtering process much more effective and economical. This robust performance ensures a cleaner power supply, which is critical for the reliable operation of sensitive electronic circuits and systems, making it a cornerstone of power supply design in electrical engineering.